Hey class, Mr. Bean here, and this is going to be video 51, and it's going to be pre-lab 51, which is Hooke's Law, Unit 5 Energy for Honors Physics. All right, so I'm going to show you kind of a simulation over here, and what we're going to do is we're going to do the actual lab in class. So we'll kind of like talk a little bit about what Hooke's Law is. So here I have let me just go ahead and throw a mass here. This mass here is, let's say 100 grams, and the spring is hanging here, and this is what's called the natural length here. Okay, no displacement. Looks like there's a force of gravity acting this way, and there's some kind of a force acting this way, which is what we call the spring force, which we'll talk about that momentarily. So let's go ahead and kind of put this mass on here and kind of see what happens. All right, so there's some dampening here, which means that friction is going to eventually come to rest. Okay. All right, so what we have here is that looks like it's stretched some length from its original position here. Okay, so we can kind of like take a look at this here and call it mass equilibrium. So we could probably let's go ahead and use this movable line here, and it looks like it's let me put it kind of like over here a little bit, and or we can maybe put it over here as well, and we can kind of see that there's some displacement here, just some displacement. All right, so here's our spring system here, and here it is again. Here's our spring, and this here was the natural length. Okay, so this is before I put a spring on here, and let's say that this is the measurement right here. Now we go to another scenario, and we go ahead and add a spring on here, or a weight. Let's go ahead and add a weight here, and we'll call this some mass M. Over here is 100 grams. All right, so this is the new position here, and let's go ahead and kind of go like this here. And this is what we'll call delta X, change in position. Okay, now right now it's in equilibrium. So if I look at this point right here, and let's go ahead and mark it right here, this position right here, we have a force, so we'll call this maybe what, mg, going in this direction, or we'll maybe just call it the force of gravity. Okay, there's a force of gravity here, and then there's some kind of restoring force that's going in this direction. So, okay, and this restoring force, we'll just call it F of the F, force of the spring going in that direction. All right, so what Hooke's law is, it's the force of the force wanting to restore this mass back to its original position. Okay, so we have a force here, and this Hooke's law force is that the spring here wants to make the mass go back to its equilibrium position. So it's in this direction. Okay, so usually what happens is that the way we describe this is that there's going to be like a minus sign here, and there's this little k, and here we'll have what's called delta x. This is the change in position. So the negative sign just means restoring force, restoring back to its normal position. In normal calculations, we ignore this, but technically it's a negative sign to show it's restoring force, going back to its original position. All right, so we could maybe rewrite here Hooke's law like this here. And here we have a delta x, and then we have this looks like a constant k here. Okay, so we want to figure out what is this k, or what does this mean? Okay, all right, so the way to do this is let's go and just make a table. So let me go ahead and let me remove this real quick, and let me make a table here, and we'll call this table delta x here. And and we'll call this a force here. And the force here is going to be what, mg, right? Mg. Okay. Or actually, here, let me go ahead and kind of, okay, we'll make this a mass. Okay, and then of course we'll want to make the mass, multiply it by g to get the force. Okay, all right. So when we first do this here, there's no displacement. There's no mass and there's no force being added. Now, consequently, this is in centimeters and this is in grams. So ultimately, this has to be in meters. This has to be in kilograms, like so. And this has to be in newtons in order for this to work out. So this would be our first point, 0, 0, 0. Okay. All right. So let me go ahead and let's just go ahead and add 100 kilograms. Okay, so I had 100 kilograms here. Now there's some dampening, which is, now if there was no dampening, this would go up and down forever. All right, so let's go ahead and see what we got here. So we have a displacement, and looks like the displacement here. Okay, so let's go ahead and maybe put this a little bit closer, maybe like about like right, see. Uh, Okay, so we're here, and let's see if I can move this spring here to right about right there. So it looks like, if I look closely here, this is 15, 16, 17, about 18. About 18. Okay, so it's 18 centimeters, which is 0.18 meters. Okay, now in the video, you may not be able to see this because this looks like it's too small here, but it's 18 centimeters or 0.18 meters, or excuse me, 0.18 meters. All right, so the mass is 100 grams, but that's going to be 0.1 kilograms. So the force is going to be 9.8 times the mass here. So we'll say 9.8 times 0.1. And that gives me 0.98. So 0.98. Okay, so let's go ahead and make this 100 grams here. Let's go ahead and maybe make this, let's say, 200 grams. Okay, so let's make this 200 grams. So now it's 200 grams. All right, so while this is resting here, or coming to rest, we'll go ahead and put down here 0.2. And 0.2 times 9.8 equals 1.96. So 1.96 newtons. Okay, now the new displacement here, let's take a quick look here. Let's go down to here. It looks like it's about 30, I'm going to say about 34. So 0.34 meters is a displacement. Okay, so we have 4 points now. We'll say 0.34. So let's maybe go ahead and make it, let's go to 250. Okay, so we'll go 0.250 here. Okay, and we'll go 0.25. Okay, times 9.8 equals 2.45. So this will be 2.45 newtons here. And let's see what the new displacement is. Still, okay, let me go ahead and increase the dampening here. So there we go, it slows down. Let's go ahead and come down here now. And according to this now, it's about 42 and a half. So we'll say 0.425 meters. Okay, so we've added some weight here and the spring has stretched out. Okay, all right, so we have this relationship here. Okay, so now let's go ahead and make a graph of this. Okay, let's go to a quick graph here. And the thing that I'm changing here is we'll call this elongation. Okay, and it is in meters, or the stretch. You can say stretch or elongation here. And here we'll say this is the force. And we want the force here to be in meters. All right, so first point is going to be 0, 0. Okay, the next displacement is 0.18. Okay, and the force is 0.98. Okay, the next displacement is 0.34, and this will be 1.96. Good. And then we have here what's 0.425, so 0.425, and then finally 2.45. Okay, so it looks like kind of so here's our graph here. It looks kind of be linear. So let me go ahead and do a curve fit, and it appears to be linear. Okay, so it's linear. And so linear equation, so we know from linear equations that we have here y is equal to mx. Okay. All right. So now here was Hooke's law up here. It said the force of the spring equals K times delta X. Well, this is going to be the force of the spring here. Okay. And this is going to, of course, obviously delta X is here. It looks like the slope is going to be K. Okay. So in this case, what is K? So take a look here. So K looks like to be the slope. So let's take a look here and see what the slope is. So the slope, okay, this is y equals mx plus b. So we can kind of ignore the b here and take a look at the slope here. It looks like 5.9, we'll say 5.8. Okay, so 5.8 is the slope. So the slope here is 5.8. Okay, now according to our graph, this should be, hold on, force should be in newtons here. This should be in newtons. Okay, so it's newtons. So it looks like Nm. So the units of the spring constant will be newtons per meter. Okay, newtons per meter is the or is this K value. So what is the K value? This is what's called the spring constant. It is unique for any spring system or for any spring. Okay, so spring constant tells you how hard it is or how easy it is to stretch or compress a spring. Okay, so this is called the spring constant. And so each spring that you ever hold or touch will have its own unique spring constant value. Okay, so this is the basis of Hooke's law. Okay, all right, so let's take a look at this in more detail here. Okay, force of the spring equals K delta X. Okay, so let's look at this formula in its full expansion. So to calculate this here, we just did simply mg, right? That was mg equals, this here was K, and delta X, isn't that just, is the final X position minus the initial X position. In our case, XO was 0. Okay, but sometimes XO is not 0, and we have to subtract from a baseline or from a starting point. So in our case, XO was 0, but sometimes it's not 0, so we have to make this a subtraction here. All right, so this will be kind of like a formula we'll be using in the lab today for Hooke's law. So one of the things we'll be doing is trying to determine the spring constant. Okay, that's right here. All right, so now let's talk a little bit about potential energy. Okay, so you have a spring system here, and when a spring is stretched or compressed, it has the ability to do work. So there is some potential energy for a spring. Okay, and let's see, hold on, energy. Okay, some potential energy. So let's kind of see what that potential energy is. So I go over here and take a look at this this graph here. So here's force, and over here is elongation. Now take a look at this. Does this look like a triangle here? Okay, so what's this area underneath this triangle here? So if I have a graph over here, and I have force here, and over here I have delta X, and I have like a line like this, what is this here? It looks like this is a triangle. Okay, and the area of a triangle, okay, area of a triangle isn't just 1/2 the base times the height, right? Okay, so let's see what we got here. So we have the 1/2 here. Okay, now what is the base? Base looks like it's just delta X, right? And what is the height? Height, of course, is the force. Okay, now what is the force? Okay, the force is Hooke's law, which is back up here. It's K delta X. So let's go ahead and substitute in here K delta X, like so. All right, so now what we have is, this is 1/2. Okay, so it looks like we have here, we're going to move the K out, and we have, looks like we have delta X squared. Okay, all right, so, okay, we're doing good here. So let's take a look at the units here. Okay, so the spring constant here has the units of newtons over meter, right? And this is delta X squared, which is meters squared. So if I look closely here, we can see that one of the meters cancel out here. So we just have Newton meters. So Newton meters is also another unit for joules, which is a unit of energy, joules. All right. So what this is then that this is a formula for the potential energy of a spring. So we will use U for potential energy and little s here means for the spring. So this is a potential energy of a spring and essentially is just the area under the curve. All right. That will conclude this video and there'll be some post-video questions. All right. Take care.